Hello everyone. Recently I made a video on the two types of Mars lander, one that was more of a conical shape and one a lifting body shape. And the purpose was for them to slow down in Mars's really thin atmosphere, 1% the density of Earth's, and use that as much as possible despite the fact that it is so thin. And that would save fuel so that they don't have to use a lot of fuel in order to land. Though you could still use propellant to land, but of course that's much heavier. You're going to be burning like half your mass in propellant in order to slow down. So it's better to just shape your vehicle in the right way to get a lot of drag to slow down. And then they use a whole lot of other stuff like air brakes and parachutes and stuff like that, balloons somebody mentioned. All these things in order to try to slow down. And now it is time to take a look at the math of going through an atmosphere, slowing down, or actually generating lift as well, because they're two sides of the same coin. And so we have here the drag equation. Now, it's not my expectation that you're going to be calculating this for everything. You know, you would probably want a sort of wind tunnel to figure out the drag coefficient. You'd have to have some apparatus. You might need some software to do this to help you out. But it's useful to analyze at least one part of it in order to figure out what's going on with your designs. So I'm assuming that either in Kerbal Space Program or in some other program you're trying to design a spacecraft. And then you're going to be able to analyze that spacecraft to see if what you've got is good enough. So it could be that you're designing it for a science fiction purpose or outside of a program, and that's fine too. There's a general purpose sort of video. So what we have here is the force of drag on your vehicle is equal to 1/2 the drag coefficient, which is dependent on the shape of your vehicle with a little asterisk on it, and then the surface area of the vehicle, which we will try to hold constant in this case, times the density of the medium, in this case the atmosphere, but it could be any other fluid, and then the velocity through that fluid or medium squared. So what we see is that the force of drag here is going to be very sensitive to the velocity, and the velocity is going to be constantly changing. The drag itself is going to be changing the velocity as we go along. So for every tick, we'll be calculating the drag, and then the drag itself will be applying a deceleration to our vehicle, so it's going to change the velocity. And so this all ends up to be a calculus thing. And we don't want to have to deal with that when we're trying to design our vehicle, because we don't exactly know what our trajectory might be yet until we've nailed down a few other things. And those are the things that aren't going to be changing during our descent. And so that ends up being the area here and the drag coefficient. However, if we're talking about our acceleration or deceleration, there's also our mass. The mass is currently bundled into the force here. Force is equal to mass times acceleration. So we would like to isolate the mass and get it onto the other side of the equation instead of having it on the left-hand side, so that we can just have the acceleration/deceleration on the left-hand side. And so we get this equation. This is the drag acceleration or deceleration. And so we're dividing the right-hand side by our mass, and instead of just putting it underneath everything, I've sort of done this, which, because of the way multiplication works, is the same thing. So we're going to bundle this together, area divided by mass. So there's the surface area divided by the mass of our object. And I've said that as long as we're not deploying parachutes or air brakes or something like that, we're going to have a constant shape hitting the atmosphere when we're trying to think about this, and we'll just deal with other things that are going to be deployed midway separately, like the parachutes. And so we're in one configuration in this, so our area is going to be the same. Technically, we could pitch up or down as well, but if we're going to do that dynamically, we'll just bundle it in with the coefficient of drag instead of trying to change the area here. So the coefficient of drag will be a proxy for our shape, and that will include, our pitch with respect to the airflow, though we would generally like to just keep it constant, and so we'll have a constant surface area, and this isn't going to change much either. But we could, make the coefficient of drag variable, and then we'll separate it off. We'll see that in a sec. But the goal here is to have something constant with which to analyze our design. So the density of the atmosphere is not going to be constant as we go down. The velocity is not going to be constant as we go down. And maybe or maybe not the coefficient of drag will be constant. There is another complicating factor in that we're going to be going supersonic. And so that affects our drag in different ways. Like going transonic will have a huge spike in our drag. That all gets bundled into the coefficient of drag as far as we're concerned. So if you take a look at in Kerbal Space Program, which is the simulator that I use, the coefficient of drag with Ferrum Aerospace Research, which is a aerodynamic mod that I use with it, the coefficient of drag will change dramatically as we're going through Mach 1. And so it is also bundling it in with the coefficient of drag. So yeah, that's what we're going to do with it. And so the constant bit is this area divided by mass. And so we define this ballistic coefficient, and we can define it either of two ways. It's usually defined flipped. So mass divided by area rather than area divided by mass. So if you do it this way, you can either have the coefficient of drag part of it, multiplying the area and in the denominator, or you can just have mass divided by your surface area. And so then you can analyze your design like that. And so the higher the ballistic coefficient, the less drag you're going to get. So if we look here, if it was flipped around, if you use area divided by mass, then the more of that you have, the more drag you get. But because we're flipping like this, it's the inverse. But this is how they usually define ballistic coefficient. So that's not my fault. But if you want it to be a direct relationship instead of an inverse relationship, you would say take your area, divide by mass, and then that's going to be your proxy for deceleration. I actually still use the official one personally. So I just keep it in my head that I want to minimize this if I want to get greater deceleration. So I want this ballistic coefficient to be low. If it's high, we're not going to be slowing down. If it's low, we're going to slow down more. But we don't want it too low. If we've got it too low, that means that we've got all these air brakes or extra surface area that we don't need. And we really want to cut it as close as possible so that we are slowing down enough, but we're not slowing down that quickly because then we've got extra mass for no reason. And it's a weird thing. The surface area is extra mass. It's just that it's mass for one purpose, which is to slow down, as opposed to the mission mass. So you could think of the mass up here as having two parts. There is the mass that we are using to help us slow down, and then there's the mission mass. If you're increasing your surface area too much to try to limit the ballistic coefficient because you want this number to be low, then you're increasing the mass to slow down, but then you're limiting your mission mass, the useful mass of the vehicle. So that means that you've got a big heat shield, but then you don't have much on that heat shield. Or you have a big surface area with a lot of heat tiles like the lifting bodies would have, but then your mission mass is very low. So we analyze our vehicles like this, and to give you an example, when I'm designing space planes, I look at the space shuttle, and I calculate this ballistic coefficient for the space shuttle. I see its mass is about 80 tons, surface area, let's say it's 1,000 meters squared. So then I take the 80 tons divided by the 1,000 meters squared, and I say, okay, it's 80 kilograms per meter squared. And then I try to design my own space planes to have the same ballistic coefficient, so that I know that my space planes are going to slow down just like the space shuttle does. Okay? And so this works for low Earth orbit re-entry. It works for Mars entry. So you'll take a look at other Mars landers, like the ones that deliver our rovers. Okay, well, they can do that. But they're actually coming in straight from Earth. So you don't need it to be that high, that low a ballistic coefficient let's say. The ones that deliver the Mars rovers actually have a very low ballistic coefficient. You don't need to go that far. But you can, if you're going to come in direct, use that as an example, or you can just do some testing in whatever simulator you want to try and match the ballistic coefficient once you have a vehicle that seems to survive, right? So let's say in Kerbal Space Program, you have a vehicle that seems to survive entry into Mars and do what you want to do. Then make note of its ballistic coefficient, and then any other vehicle that you design with the same ballistic coefficient should have the same property, as long as it's not a wildly different shape. As long as it's not a wildly different shape, because then that's the coefficient of drag, right? So also, you will be able to tell if you're aero capturing around Mars that you need to be at a certain height for a certain ballistic coefficient. So when trying to figure out aero capturing with Mars, what I did was I had a certain ballistic coefficient vehicle, so it had a certain mass and a certain surface area, and I noted what altitude it needed to be in order to capture around Mars. This is not coming down. This is just aero capture. So we're coming in from Earth, and we're going to use the atmosphere to get us into orbit. But we don't want to go far. We don't want to crash into the surface, and we don't want to be too high, because then we'll just skip out and go into interplanetary space. So we have to hit the right altitude, and it's basically a 5,000 meter window in altitude that will let you capture. And ideally, you'd want to capture into a nice low orbit so that it's more convenient. But using the ballistic coefficient, you can figure out what altitude you need to be at in order to capture. And then everything with the same ballistic coefficient, as long as it's coming into Mars at the same speed, right? It's still sensitive to speed. So if you're coming in too fast, you are going to have a problem. As long as you're coming in at the same speed, hitting the atmosphere at the same speed, then then you have the ballistic coefficient being the same, then you'll have the same capture altitude. If you're coming in faster, of course, you need to go lower in the atmosphere. If you are coming in slower, you go higher in the atmosphere for the same ballistic coefficient, and I essentially have a table of these things. So that's all ballistic coefficient, but it is also related to lift. So if we take a look at this, ballistic coefficient is BC equals m over a. Well, let's take a look at wing loading. Wing loading is a measure of how effective an airplane is, and it determines what your stall speed is going to be with the plane. So the stall speed is going to be higher for something that has a higher wing loading. And so the wing loading is the mass or weight. It's usually defined as the weight of the vehicle, but that's a little bit weird for us because the weight is force. And if we go back to the original equation, then what is the unit for lift? It's actually a unitless thing. So we want to sort of think of it as an acceleration still. And if we want to think about the lift as an acceleration, we'll stick to mass. And so mass over wing area is the wing loading. So that's very similar to the mass over surface area. So how does that work for the space shuttle, right? Well, the space shuttle shape has a different drag coefficient than it has a lift coefficient. So if we go to the full lift equation, we see that there's a lift coefficient. That's not the same as the drag coefficient. And so the shape of the space shuttle in relation to drag is different from the shape of the space shuttle in relation to lift. Well, I mean, when coming down, it will both lift and drag help it. So they both contribute to slowing it down. But ultimately, if it were try to take off, it never did, then we would have a problem. But airplanes, for instance, the lift equation is dealing with the shape of the airfoil, whereas the drag equation is dealing with the shape of the entire vehicle that is being forced to slow down. Drag and lift are not opposite each other. Drag is opposite of thrust, so it's slowing you down. Lift is opposite of gravity. So lift is counteracting your gravity, drag is counteracting your thrust. So lift and drag are not working against each other. So this is all allowed. But there are times, but then you have to worry about the drag is slowing the velocity down, and if it's slowing the velocity down, the lift equation, which looks practically the same, has a velocity in it. So then the drag is actually reducing your lift in that respect because it's reducing the velocity. So it's complicated. But what's not complicated is the fact that we basically have the same equations working through for both drag and lift. So you can analyze lift and drag with the same basic thing, which is mass divided by surface area. And so in the atmosphere, if you're trying to decide whether your plane is going to be able to take off at a certain speed, then you are going to take a look at its mass divided by wing area and compare it to other planes that have a similar mass on the same wing area. So in theory, though this doesn't always work in Kerbal Space Program, if your plane has the same wing loading as another plane, and their wings are shaped the same, the coefficient of lift is the same, and the body is not some grotesque shape like the pregnant guppies, the super guppies, something like that, then the takeoff speed should be comparable. That's the idea. So we can compare vehicles in the same way, cross-compare them, just like we're doing with the drag. So the whole business of designing an aircraft is also very similar to designing an entry vehicle for Mars or Earth or something like that, or Titan, for instance. And that's part of where we get the lifting bodies from, right? Because we have both drag and lift so closely related, sometimes working together to do something like slowing us down. This will keep us higher up in the atmosphere while drag is slowing us down. It's all complicated, but it's all one neat package. And all you have to remember is analyzing the mass divided by surface area. So you can compare vehicles like that, and that's the gist of the video. We take a look at different vehicles, compare them, and then we can get our design. Because so much of the work has already been done for us, it would be silly not to make use of that. So that is the video on ballistic coefficient and wing loading. There's plenty more to say. There are college courses on these types of things, so I'm just scratching the surface, but hopefully it gave people an idea. So with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.